Alaska's Arctic frontier is one of the most dynamic and rapidly changing regions on Earth. Across the Arctic, permanently frozen soil, called permafrost, stabilizes infrastructure. It supports heavy loads and prevents erosion as if it were concrete. But as that frozen foundation softens, the land can sink or shift vertically, sometimes just by a couple millimeters, but sometimes by feet. The sinking doesn't happen uniformly either. Some areas sink much faster than others. This differential settlement is a wild card for infrastructure, affecting things in unpredictable ways and making it more vulnerable to erosion, flooding, and slope failure. Pipelines are strained, power lines will either sag or snap, and roads may be washed away. And when the ground starts to move, other geohazards soon follow: erosion, flooding, and slope failure. For the Department of Homeland Security, it's a mission issue. Because when lifelines fail in Alaska, response operations slow, supply chains are cut off, and the ability to protect the Arctic is weakened. Recent storms like Typhoon Halong have made that reality impossible to ignore. When Halong struck western Alaska, it didn't just bring coastal flooding, it exposed how vulnerable the terrain itself has become. Communities that were built on permafrost experienced severe subsidence, and that amplified the storm's damage. That's where our project comes in. Through the ADAC-ARCTIC program, Dewberry, Boston Geospatial, and Virginia Tech have partnered to create a new monitoring and modeling capability for DHS.
In order to map a region, we are using interferometric synthetic aperture radar, which is also known as INSAR. This uses satellite radar imagery to measure ground motion with millimeter-level precision.
By comparing the phase of radar signals acquired over the same area at different times, we can detect vertical movements of the ground, such as uplift or subsidence. When we process stacks of these images, we can attain a continuous time history of surface deformation instead of just a static elevation snapshot, which is what LiDAR data provides. With INSAR, we can understand the rate of ground motion over the past decade, whether it's subsiding at a constant rate or perhaps accelerating. And then we can project that into the future to forecast for things such as infrastructure replacement. INSAR analysis also shows that ground motion isn't occurring uniformly. There may be pockets of stability or areas of rapid subsidence, all of which are important considerations in the Arctic domain. Our project develops a full INSAR time series over high-priority existing and future infrastructure areas in Alaska, identified via our engagement with DHS and its components operating in the region. We transform those measurements into easy-to-use ground motion products, capturing both long-term trends and seasonal changes, and we feed them into two core models: a slope risk digital twin and a permafrost stability model. This capability is critical for the Arctic, where DHS and other state and federal agencies depend on infrastructure that's increasingly threatened by erosion, flooding, and thawing permafrost. Yet today's assessments still lack the historical context needed to quantify and act on those risks. Our approach fills that gap and converts it into actionable intelligence, revealing which slopes and corridors carry the highest risk, and which facilities, transportation routes, and lifeline systems must be prioritized.
For example, knowing that a runway is slowly subsiding long before it becomes unusable, or identifying that a section of coastal roadway will likely erode in the next storm surge. This project converts cutting-edge science into operational geohazard intelligence. It expedites timely decisions for DHS operators and planners. It protects critical infrastructure. It supports FEMA's mitigation priorities, and it strengthens Arctic domain awareness across all DHS missions. We're delivering these insights through interactive dashboards and story maps built on the ArcGIS platform. These tools translate complex satellite data into clear visuals that decision makers can access directly, hosted by the Alaska Geospatial Office. In just a few clicks, they can see where risk is increasing, compare it to their assets, and plan accordingly. Beyond infrastructure protection, this project also helps FEMA and other resilience planners identify where mitigation dollars will have the greatest impact. It helps CISA prioritize critical infrastructure investments. It helps the Coast Guard better understand how permafrost degradation and coastal erosion might affect navigation safety and station access. And it helps CBP plan for long-term operational resilience across remote Arctic installations. But the impact of this project goes beyond agencies and data layers. It's also about building human capacity in the Arctic. Students will be embedded in the research. They will learn to process INSAR data, to develop GIS applications, and to communicate technical results to communities. These students represent the next generation of Arctic scientists and decision support specialists. The skills they're gaining now will strengthen both the science and the Homeland Security mission for years to come. This project represents a shift in how we approach Arctic hazards. Instead of reacting to disasters after they occur, we're enabling proactive resilience, a way to understand, foresee, and mitigate the cascading effects of permafrost thaw, erosion, and storm damage before they impact lives and missions. For DHS, that means greater Arctic domain awareness, stronger infrastructure protection, and improved supply chain continuity across America's northernmost frontier. It's about ensuring that Coast Guard cutters can reach their stations, that CBP radar networks remain operational, and that FEMA can move quickly when communities need help. Ultimately, this project turns the ground itself into an early warning system, a way to hear what the Arctic is telling us before the next storm hits. By leveraging the power of satellite radar, physics-based modeling, and infrastructure owner-operator partnerships, we're giving DHS the ability to see risk forming and the foresight to act on it. This is how we make the Arctic more resilient. This is how we strengthen the homeland. And this is how science directly supports national security. Together, we are turning data into action, action into preparedness, and preparedness into protection for Alaska, for the Arctic, and for the United States.